already mentioned about the subordination of Brownian motion and beta stable subordinator. I will verify it right now. So, example here, which corresponds to this statement. So, as a Levy process, for example, as a Levy process, I take Brownian motion. That is its symbol, psi of p is equal to, okay, p square. I kill 1/2. We don't need to care about this 1/2. It depends on how we define the motion. So Brownian motion, which is twice fast or twice slowly. Then as a subordinator, I consider this beta stable subordinator. That is the corresponding Bernstein function is just zeta to the power z to the power beta. Beta is between 0 and 1. And hence, if I consider this time-changed process, C zeta t, so it has the symbol f of psi of p, which is p squared to the power beta. But then this is just p to the, so norm of p to the power 2 beta, and this is exactly the symbol of 2 beta stable and symmetric Levy process. So we discussed yesterday that a Levy process with such type of symbol is called symmetric alpha stable process, for alpha equal to 2 beta in this case. So you see you have a Brownian motion with continuous path. As a random change, you take this beta stable subordinator, and this time change process now has parts which have only jumps, because this guy with this process, so particle moves only by jumps. There is no continuous path. Okay. So we are finished so far with the topic subordination, but we will need it tomorrow, today and tomorrow in the sequel. Now I kill my... Oh, I have forgotten to use my microphone. But do we need a microphone actually? No. I can cough without microphone much more than the cough. So let us go further. And we start lecture 4. The slides are as it was planned in advance for lecture 4, but we discuss as much as we will be able to discuss. Okay, so the topic of this lecture is Chernoff approximation. So I recall you that there are many different approaches to construction, approximation, and representation of strongly continuous semigroup. And I said that Chernoff approximation is a very broad, very general, very broad generalization of this formula, which you should know from the first year of analysis. Okay, so let us go into details. So what I'm going to tell you is given in this survey paper, the method of Chernoff approximation, and in a more detailed version, it is given in my habilitation. It is also available online at Stanford University in Georgia. we discussed Chernoff approximation. So I recall you the setting. So if we have a time homogeneous Markov process, that is the process which has no memory, then the most important characteristic of this process is its transition kernel, P Tx dy, which gives us the probability of a transition from point x to some set dy, when we have t units of time for making this transition. So as soon as we have transition kernel, we can construct integral operators, and by the Chapman-Kolmogorov property of transition kernel of a Markov process, this family of operators is a semigroup. If this semigroup turns out to be strongly continuous in some reasonable Banach space, then the function which is given by means of this semigroup, in one hand it has this stochastic representation, on the other hand it solves the evolution equation with L here, which is the generator of this strongly continuous semigroup. So this all we have discussed already on the first lecture. So roughly speaking, we have three more or less equivalent problems. So in terms of stochastics, our aim would be to determine the transition kernel Ptx dy for a given Markov process. In terms of functional analysis, it is equivalent to constructing a semigroup whose generator is given in advance. And in terms of theory of partial differential equations, this is equivalent to the task to solve the Cauchy problem for a given partial differential equation of this form. Okay. So, example, which is positive example in all senses, that everything is doable in a pleasant way, and we have done it yesterday. So if we have heat equation, then the solution to the Cauchy problem is given in terms of heat semigroup. This is a family of integral operators with Gaussian kernel, and this Gaussian kernel is the transition kernel of stochastic process known as Brownian motion. But the problem is that usually the transition kernel of Markov process cannot be given explicitly in an explicit way, and hence the semigroup is not known explicitly. So the task is to if we don't know the semigroup explicitly, we know that it exists, but we have no explicit form for that, then we can try to approximate it by something which has some explicit form. So this gives rise to Chernoff approximation. So the aim is to find a family of operators, bounded linear operators, which are not a semigroup. It's a disadvantage, but they are known explicitly, so they have some explicit form. And to find this family such that the following identity holds. So in order to get the action of the semigroup, we just apply this f iteratively. So when n tends to infinity, this stuff should converge to the semigroup which we don't know. And it should be true for any f0, for any element of our Banach space. So, in a sense, this family is approximating family for my unknown semigroup. So how to interpret this identity? So this identity is called Chernoff approximation. So in one hand, this gives rise to a numerical schemes for the corresponding partial differential equation. Namely, so I recall that the corresponding partial differential equation is df over dt is equal to LF, and we have initial conditions. F of 0 is equal to F0. And we have this Cauchy problem. So how we solve it? So we split our time interval. So we make equipartition. So we split it into equal parts. Each part has the size t over n. And we do as follows. So we construct an approximate solution. So U0 is the same as F0. So here we have F0 in this point. This is what is written here. Then in the next time step, we apply, so instead of unknown semigroup, we apply the known family of operators. And we obtain U1. Well, this is something else. This is not the true solution, but it is something else. Yeah? Then in the next step, we again, to U1, we apply this family F at time point T over N, and we obtain U2. And so on and so on. After N steps, we obtain UN, which is an approximation for the true solution F of T. So this identity guarantees us that if if step N tends to infinity, that is, the partition is going to be finer and finer, smaller and smaller, then this approximation tends to the true solution. So this is actually nothing else but the Euler scheme for this ODE. But this is a Banach space valued ODE. Yeah? And that's why there are many different families which are suitable for this Euler scheme. Okay? So Chernoff approximation is the Euler scheme for Banach valued ODE. And hence, it gives us, so for each family F, which fits to this formula, we have a particular numerical scheme for the given Banach space valued ODE, that is partial differential equation, or pseudo-differential equation, integral differential equation. Okay, so these are numerical schemes for evolution equations obtained by time discretization. Moreover, if our semigroup has a stochastic interpretation, that is, if there is a Markov process behind it, then this time discretization also gives us a kind of approximation of a Markov process by a sequence of random variables sometimes.
So the capital F is supposed to be a linear operator.
Yes, family of bounded linear operators, but without a semigroup of it. So this is a picture which says that if TT corresponds to some Markov process, so I have drawn here a path of a Markov process, psi t, then this time discretization, so as before, we consider this time discretization, and at each point t over n, we have some random variable, probably, if these operators also are related to some random variables. This is written here, so if my family f of t is such that we have something like this, then we roughly speaking, we have a Markov chain approximating my Markov process. And moreover, if this Markov process is a solution of a stochastic differential equation, then this Markov chain approximation is nothing else but Euler scheme for SDE. Again, Euler scheme, but SDE. I will clarify, everything will be clarified by examples. So now it's just general discussion, everything is very abstract, but then we will see some examples, and you will see how it works. So Chernoff approximation gives us numerical schemes for PDEs, numerical schemes for SDEs, and also if the semigroup has a representation in terms of some path integrals, like Feynman-Katz formula, it is an integral over some path space, this dimensional space, then the right-hand side can be understood as approximation of a path integral. Or sometimes it gives rise to new path integral representations. So there's three aspects of Chernoff approximations. We will clarify all of them in the simple. So this is the simplest version of the Chernoff theory. There are, of course, many generalizations, more advanced versions, but this is the simplest one. So let Tt be a strongly continuous semigroup on some Banach space with some generator. Let f of t be a family of bounded linear operators satisfying these three properties. So if these three properties are satisfied, then we guarantee that the Chernoff approximation holds. And moreover, the convergence is locally uniform with respect to t. That is, for t on compact intervals, this is uniform with respect to t. So now let us see, look more carefully at these three conditions. So as I said, this family does not need to be a semigroup. So we have a semigroup, but we don't know it. It does not have explicit form, explicit representation. Instead of that, I consider a family of operators, which are not a semigroup, but f of 0 is identity. So this is the same requirement as for semigroup. So tt at t equal to 0 is also an identity. Yes? So the third condition, the derivative at 0 is n. So this is the same requirement as for the semigroup. The derivative at 0 should be n. Okay, if not on the whole domain, but at least for an essential domain. So these two conditions actually say that, in a sense, this family, this function of t, in a sense, tangential to this function of t at point 0. Yeah, we usually say that family is Chernoff equivalent to the semigroup. So the idea is that these two requirements say that, okay, at 0, these two guys are similar up to the first order. Okay, and then this requirement, it is a technical requirement that the norm of these operators cannot grow too fast. Okay, so actually these two things, they are a kind of consistency conditions, and this condition is a kind of stability condition, and there is a kind of meta-theorem in numerical analysis which says that if we have a consistency and stability of a numerical scheme, then we have a convergence of a numerical scheme. So this is a kind of interpretation. Okay, now let us look more carefully in the statement of the theory. For example, if my n is the generator of my semigroup Ct is bounded, then I can consider the following family of operators: identity plus Tn. Of course, this is not a semigroup. Of course, f of 0 is just identity. Derivative at 0 of f is just n. Yeah? And this estimate for the norm is also satisfied. So this family is perfectly Chernoff equivalent to the semigroup. So inserting this in this formula gives us this formula. And this is just what you know from the analysis formula, the first one of formula. Okay, so I said that Chernoff approximation is a very broad generalization of this statement.
The key assumption in this example is you assume that L is bounded.
Sure, sure. Yes.
If the L is not bounded, then
Then, for example, so if L is unbounded, let us consider this guy. This is the resolvent. So at least for small t's, the resolvent is a bounded operator. And hence, we have this formula, also known from analysis 1. But this is just one of examples, nothing else. There are many examples. This is just the simplest one.
Sorry, I just want to say this.
Yes.
So, although you assume that L is unbounded,
Yes.
so because the generator actually that's a semi-bounded from above, right? So that's you take that advantage
Yes.
to do that.
Yes.
If that's not the case, you cannot make this kind of
Well, if it is a generator of a semigroup,
Yeah, that must be bounded
it should be
from
closed.
above.
No, but it is
Because
closed and densely defined. And from the here you see the theorem which we had no time to discuss. Wait. So for any semigroup, we have stated it that for any strongly continuous semigroup, we have this type of estimate for some m and omega.
Yes.
Or W. Then it turns out that this array lies in the resolvent. So for small t, 1 over t is already here, so in the resolvent, so everything is fine.
Okay.
But we have not discussed it, of course. Yeah, but this is just one example. Because you know, it's nice to have this formula, but for that we have to know resolvent explicitly in order to use it. And this is also an issue. That's why it's nice to have some other families. So it's a nice formula, but we don't know resolvents usually. Okay. So yeah, I'm trying to advertise the so-called Lega principle for Chernoff approximation, which says that. So let us obtain Chernoff approximation for different operations. So we start from some simple semigroup with a simple generator and assume that we know the semigroup explicitly, or we know how to approximate it. So we know the corresponding family, which is Chernoff equivalent. Then we make some operation on the operator and obtain another operator and hence another semigroup, probably more advanced semigroup. And then the question is how to obtain the Chernoff approximation for the new semigroup. So if we answer this question for many different operations, then we can use it like a Lega constructor. We start from something simple, and then make one operation, another operation, and so on and so forth, and obtain more and more advanced semigroups, and automatically obtain their Chernoff approximation. I'm sorry, I have used too much chalk. So we can start from some simple processes or simple operators, which are, for example, the processes with known semigroups, or processes with known transition kernel. There are some of them, and even some new processes pop up, so new formulas for kernels pop up. So it's nice to start with a process or operator which corresponds to a known semigroup or known submarkov kernel. Or it is nice to start with a process or operator whose semigroup or whose transition kernel is already Chernoff approximated. In particular for failure processes, PRD, you know Chernoff approximation. For Brownian motion in a compact Riemannian manifold, we know different Chernoff approximations. And even for failure diffusions in Riemannian manifold, we also know some Chernoff approximations. We are just a kind of list of results which are related to that story. So we start from a nice process or from the nice operator, from the nice semigroup, and then we apply some operations to construct more advanced semigroups. So which operations are already considered in this setting? So Chernoff approximations are known for the following operations. Operator splitting, that is, if we have some easy terms and then consider their sum, and then the more advanced operator is just the sum of simple summands, so to say. So this is possible. Then averaging of generators. So we have a family of generators of strongly continuous semigroups. So each strongly continuous semigroup is already Chernoff approximated or known, and then we consider this averaging procedure. So we just average with respect to some measure on some parameter set. And if this guy does generate a semigroup, strongly continuous semigroup, how to obtain Chernoff approximation if we know them for these guys. So I feel the chalk in the air, I'm sorry, this makes me cough. Okay, we know Chernoff approximations for subordination, for rotation, that is, like from heat equation we go to Schrödinger equation, and for two things which are related to considering processes or operators in bounded domains, or not necessarily bounded, but in domains with some boundary conditions. So if we have directly a boundary condition, then it corresponds to killing. If we have some other Robin boundary conditions, it corresponds to oblique reflection of the process from the boundary. So some Chernoff approximations for these situations are also known. Okay. So here are some references concerning these the results, the corresponding results. And now we will discuss some of these things. Let us start with operator splitting. So we consider the operator L star, which is obtained by a sum of operators. And we assume that L star does generate a strongly continuous semigroup. And we consider some set, which is a core of this generator. And we assume that on this core, my L star has this representation. It is a sum of simple terms, and we do not require that any of these terms does generate any semigroup. These are just sum of some operators. Assume we are ready to construct, assume we are able to construct families of operators Fk, such that each family works with each particular summand here. Namely, each family should satisfy assumptions of Chernoff theorem, that is, at time 0 they are identity, the norm estimate is as in Chernoff theorem, and the derivative at 0 gives us a particular summand here. So we have Fk for k equal 1, 2, 3 up to n. And this identity holds on this core. Then we just consider the composition of these families. This is a new family of operators, and the statement is that this guy is Chernoff equivalent to the semigroup generated by L star. Let's chalk here. Well, it is an exercise to check that it is So you see that at time equal to 0, this operator f star is identity. The norm of this operator f star is also bounded by some exponent times t times constant. Exponent to the power t times constant. And if you calculate the derivative by just using the chain rule, you see that the derivative is the sum of derivatives of each fk. So we obtain exactly L star. So all requirements of the Chernoff theorem are satisfied.
I have a question.
Yes.
Perhaps because I missed your first talk. So the form of exponential function of a generator, we know that I know that when you are consider the self-adjoint or symmetrical case, that makes sense. But in general case, there are some steps to make sense of this expression, right?
So we just define the semigroup as a family of bounded linear operators having the following properties. They are bounded, linear, t at 0 is identity, t composed with ts is t plus s, and that's all. They are semigroup. Then they are strongly continuous semigroup if tt phi tends to phi, the identity pi to phi, then t tends to 0 in the norm of the bounded space. So if it is so, we are able to calculate the derivative at 0 here. And it will be the operator L. So it is limit t tends to 0, tt phi minus phi
Yes.
over t. This is L phi, but it does not need to exist for all phis.
Yeah.
But we know that if we have a strongly continuous semigroup, then there is a result, then the generator exists, and it is a closed, densely defined operator.
Right.
That's all. It does not need to be symmetric.
Right.
And we are in the Banach space.
The problem is how you make sense of this exponential function of L. So
No. I do not make sense of exponential function of L. I just say that if we start from here,
yes.
we go to L. If we start from a strongly continuous semigroup, we can obtain its generator. And then we can understand Tt as a subject that replaces this object.
Okay. So basically.
So this is a formal notation
Okay. I see.
to specify the generator.
This Chernoff approximation basically is a way to approximate the generator.
To
Yeah,
semigroup.
Yeah, that makes sense. Thank you.
Yeah, so here, once again, this is just a notation for the semigroup with generator and star, nothing else. Classical formula known already almost for a century, the Leski-Rotter formula. In this case, it is assumed that L is the sum of two summands, and each summand does generate a semigroup. Then I can consider this composition. So this is my F1 and this is my F2. And the composition of semigroups, the composition of these two operators does not need to be a semigroup. So if L1 and L2 do not commute, this composition is not a semigroup. But it is Chernoff equivalent to the semigroup generated by the sum and has this formula called. This is the Chernoff approximation. Okay? One more example. Again, we consider the case that we have only two summands. Assume we have constructed F1 and F2 such that this holds. Then I can construct some new families which are Chernoff equivalent. So one is just F1 composed with F2, but of course it does not matter in which order I make this composition. I can also F2 compose with F1. So the ordering here does not matter. So I can consider F1 composed with F2, or F2 composed with F1, or just a mixture of such two orderings. So for any tau here, we obtain a family which is Chernoff equivalent to the semigroup. Moreover, I can do even further. I can apply a little bit of F1, then I apply F2, and then apply the rest of F1. This is written here. So here T, here a little bit less than T, here T, and here again a little bit less than T. And again I obtain family which is Chernoff equivalent to the semigroup. And of course I can create more and more advanced formulas, like we mix the ordering, how we apply a little bit of what first. In all cases we obtain families which are different families, but they all are Chernoff equivalent to the semigroup. And moreover, it turns out that, so usually Chernoff approximation corresponds to numerical schemes of order 1. But here, for theta equal to 1/2, and for tau equal to 1/2, in some cases, we obtain schemes of second order. So it really makes sense to play with the ordering. Okay. Example, we consider heat equation with some extra term, potential term. So we multiply with a function. We take a very nice function, let's say continuous bounded, and then I can show that the sum Laplace plus potential also does generate a strongly continuous semigroup on the proper bounded space. So now we just want to use this Dalevsky-Electronov formula. So the semigroup generated by this second summand is known. This is a multiplication semigroup. So we multiply it with the function e to the power t as before, as we did it at the first lecture. But the first lecture it was c of x, not v of x. But now it is like a potential term, that's why it is v. And the semigroup generated by Laplacian is also known. It's a heat semigroup. So integral operators with Gaussian coordinate. Okay, so the solution of this equation with this initial data should be given by the semigroup generated by the sum. So now we use the Chernoff approximation or Dalevsky-Electronov formula in this particular case. So we have this limit. What does mean this composition? So we apply integral operator and then multiply with the function, and then we iterate it n times. Hence, we have just n iterative integrals. And as integrand, we have, okay, so this function and Gaussian exponents, many Gaussian exponents, which correspond to transition kernel motion. So this representation, such type of representations for solutions of evolution equation, is called Feynman formula. So what is here? So here we have only integrals of elementary functions, Gaussian exponents, and this function. So this is a solution of this equation. So and you can numerically calculate everything because you have integrals of elementary functions. Everything is known. On the other hand, you can see probably that, so here we have e to the power something. So this is nothing else but a Riemann sum for the integral of this type. And one can show that this limit of iterated integrals is actually nothing else, coincides with the following expectation. So here we have our Brownian motion with the process, and we have e to the power integral from 0 to t, potential of psi s ds at 0, psi at point t. And we start the process of Brownian motion at point x0, this is exactly this point here, and here. So actually, starting with Chernoff approximation, we obtain the approximation of the solution in this form. So we obtain Feynman formula, and having this, we can show that the solution also has this form. So we have stochastic representation for the solution of this evolution equation. And this is the classical standard Feynman-Katz formula. So the semi-group here semi-group here is related to a process of Brownian motion, but its stochastic representation has not only this term, but also some extra terms, more advanced function of Brownian motion. But nevertheless. So if I know how to simulate Brownian motion, I can simulate many paths of Brownian motion, and I can numerically calculate, approximately, so this expectation by Monte Carlo. And hence I can calculate the solution. So you see, if you are able to make Chernoff approximations, this is the way to stochastic representations, this is the way to Feynman formula. So this gives the way to solve evolution equations. Now, how much time do we have? Okay, but today we have 1.5 lecture. Okay, now Chernoff approximation for failure processes. Failure or failure semigroups. They were defined yesterday. I recall what yesterday. So failure process corresponds to a semigroup, which is called failure semigroup, which is a strongly continuous semigroup on this Banach space. And whose generator is a pseudo-differential operator with symbol minus psi. Now instead of psi, I use this h, because H is for Hamiltonian. So if we consider a system, classical or quantum mechanical system, so then there is the energy of system and energy of the rate of system, they are Hamiltonian. But okay, yesterday it was just psi. So failure process corresponds to a failure semigroup, which is a strongly continuous semigroup of this space, and whose generator is a pseudo-differential operator with symbol minus h, where h for x fixed. X here is given by the Levi-Kinchi formula. So in total we have this terrible formula with variable coefficients. So if coefficients are constant, then we have a Levi process and everything is known. If the constants, this CBA and mu and it was mu yesterday, sorry. If they depend on x, then the situation is not that good. So once again, the generator is given by pseudo-differential operator with symbol minus h. And if my h does depend on both variables, we know that the semigroup Tt, which is also written here, this is the semigroup generated by pseudo-differential operator minus h, it does not coincide with the family of pseudo-differential operators with symbol minus, with symbol e to the power minus th. So here this hat means where we take what we take there. So the right hand side is the semi-group generated by the operator minus h hat. And here we have the operator, which is a pseudo-differential operator with this symbol, e to the power minus th. Okay? We discussed yesterday that they are not equal. So this guy on the left-hand side this is not a semi-group. Theorem. This is not a semi-group, but still this is the family of operators which turns out to be bounded linear and Chernoff equivalent to the semi-group. So we don't know the semi-group, but these are pseudo-differential operators with explicit symbol. They are not a semi-group, but they are Chernoff equivalent to the semi-group. Hence we have this Chernoff approximation. In order to enjoy it, we'll give some examples, of course. So first of all, I told you already that I state that this is a family of bounded linear operators. But if they are pseudo-differential operators, then it's not obvious that they can be extended to the whole power space. Yeah, so the way to extend it looks as follows. So I write down f. So by definition, it's a pseudo-differential operator with this symbol. So this is the explicit formula for the operator f of t. Yeah, as pseudo-differential operator with this symbol. Now I would like to take this part. So I would like, so to say, to take this part and add to the symbol, and I still obtain, so with plus or minus, I still obtain a function which is given, a function of this type. So there exists a measure, a subprobability measure, whose Fourier transform is given in this way. Hence, if I first, so here we have double integrals. If I first integrate with respect to p, here, I obtain the integral of this type. When I integrate with respect to p, I obtain integral of f of q, and here we have a measure which is a subprobability measure. And the right-hand side is a well-defined operator here, and it is bounded on linear. So this allows us to see that these operators indeed are bounded linear operators on the whole bound space. Example. Consider us as a symbol of the generator, so energy operator, this type. So we have a variable coefficient a of x multiplied with norm of x. So the corresponding generator, that is the operator with symbol minus h hat, is nothing else but a multiplicative perturbation of this fraction Laplacian. So this fraction Laplacian to the Laplacian to the power 1/2. So it's a square root of Laplacian. So and we have this variable coefficient. So it's a multiplicative perturbation of fraction Laplacian. Square root of Laplacian. Okay, so if we consider such h, then the corresponding f, so I just write down this formula. So the definition of f, it looks like this. And so what do I see? So I recall you that, okay. I recall you that we have discussed stable processes. Yeah. So these are processes with symbol of this type. So take alpha equal to 1, then I still have a stable Levy process with such symbol. And then the corresponding semigroup has this representation. It's a Levy process. The corresponding semigroup has this representation. That is, it has symbol e to the power minus t psi, where psi is just this normal speed. So what is written here is exactly the same, but instead of t, we have t times a of x. So I consider it as a new time. X is fixed, so just this is my new t. My a is positive. I have not written it, but it is a positive function. So this is my new time. And then for the semigroup generated by this stable process, the semigroup is known explicitly. The transition probability of this stable process is known explicitly. And it is given in terms of the Cauchy distribution, which I mentioned yesterday. So this integral is nothing else but this integral. So we integrate phi, and here stays the measure, which is the Cauchy distribution at time point a of x. And hence, so if we have this f, so in this limit I have n iterated integrals of elementary functions. So again I have a Feynman formula, which allows me to calculate the solution, to calculate approximations of the solution. Okay? Another example, non-degenerate diffusion. So we consider H in the case where my C is equal to 0 and N is equal to 0. So no terrible term, only these two nice terms, and the corresponding process is the diffusion process with continuous path, nice diffusion process. Okay, in this case, if I calculate this Fourier transform, so H is a nice function, polynomial. So the Fourier transform is very well calculable. So I know this mu x, and it looks like this. So the Gaussian exponent, yeah, with this normalization. So if my A and B would be constant, then here would be just the semigroup which corresponds to the corresponding Levy process. But since my A and B coefficients are not constants, they depend on x, this family of operators, this is not a semigroup. But we have already proved that this family of operators provides Chernoff approximations for the semigroup generated by this diffusion process. Let us discuss it in more details. So we consider this family of operators. So the statement was that this family is Chernoff equivalent to the semigroup generated by the diffusion process, or corresponding to the operator which has this form. Okay. So second order term and first order term. Diffusion reduced. So consider the corresponding SDE. dxit is minus bxit dt plus square root of 2a xi of t dwt. Here wt is the Wiener process, volume motion. Consider the Euler scheme for this SDE on the interval from 0 to t with time step t over n. So what does mean Euler scheme for this SDE? So we start, so at 0 we have the initial condition, It is not written here, but we have some initial condition. And then we approximate the increment of the process by the increment xk plus 1 minus xk. So this difference is approximation of dxit. We take left points to insert into coefficients. So we consider coefficients at left points, so bxt. So bless you. So dt is exactly the length of my time step, t over n. So this term is nothing else but this term, or approximated by this term. So this axi of t is approximated by a x of xk, so the left hand side. So okay. And how to approximate the increment of Brownian motion? So we know that increments of Brownian motion, if we have time step t over m, it is a normal random variable which is centered with variance t over m. So we can take just zk, which is a standard normal Gaussian, and multiply it with the square root of t over m to get this variables, the needed variables. So we just take a family of independent, so of IID in that case, and construct this chain. So x0 is just the initial value of this SVE. And then the next step is defined by the right hand side. It is again Euler scheme, as we have seen before, but for SDE, not for PD. Yeah. So I can return to this nice picture. Well, it was a bad idea. It is very far away. So something like this. Yeah. So this is the solution of SDE. We start from this, and in each step we define some approximation. Approximation is defined iteratively, and how it is defined, I just presented here. Okay, so this is the Euler scheme. So what is written here? So this formula, iterative formula, this is just the Euler or Euler-Mariano scheme for solving this SDE. So now we consider this a conditional expectation. So this conditional expectation, so I just insert what is xk plus 1. This is given by this formula. So I just insert it here. Yeah, and I calculate the conditional expectation. That is, I calculate expectation of this guy, taking into account that my x is nothing else but xk. Yeah, and I take into account that my zk is independent from xk. But you know that zk is IID, is a standard normal Gaussian. Yeah. So we know the distribution of this random variable. Isn't? Don't we? It's a Gaussian random variable. This is the mean, and this is the variance. Okay? Hence, this is nothing else. So the expectation of this thing, of this random variable, is just given by this integral. So what stays here, this Gaussian exponent, this is nothing else but the distribution of this random variable. Okay? So this conditional expectation is nothing else but my ft over m applied to f0 at point xk. Xk at point x, and then we insert a random variable xk instead of x. Then I can use Talbot property to calculate this conditional expectation. I just insert conditioning first on xn minus 1, then I condition on xn minus 2, then, and I come back to x0. But on each step, such conditional expectation is nothing else but f at point t over n applied to f0 at the corresponding random variable. So after inserting all conditional expectations inside, I obtain just this. Of course, it is supposed that you have ever seen the conditional expectations and all that stuff. If you didn't, then just relax and skip this part. So what I want to say is, so we have shown already the Chernoff approximation. So we know this blue limit that it's true. But the left-hand side is a semigroup generated by Markov process, and hence it has this representation. At the right-hand side, we have already calculated this guy is this conditional expectation. So the right-hand side is just this limit. Hence, from our Chernoff approximation, we obtain that the left-hand side here is equal to the right-hand side here. But this equality of these two sides means that we have proved that the Euler scheme converges weakly. Okay? So it is. So I said at the very beginning that Chernoff approximation gives us Euler schemes for PDEs, Euler schemes for SDEs, and approximation of path intervals. So now we have clarified everything, I hope. So it was supposed originally that we discussed also Chernoff approximation for subordinate semigroups, blah, blah, blah. And so you see that there are many slides. So the slides will be available, but I think it's enough for today. And nevertheless, subordination will be needed tomorrow. So it was not senseless to discuss it today. But Chernoff approximation for subordinate semigroups is constructed. So if you are interested, you can look at the slides. And I am finished for today. Thank you for your patience. Hopefully you will come tomorrow. Are there any questions, remarks, suggestions? Okay, then I suggest we go to lunch.
So the second lecture is usual as 2 p.m.